I want to do a reaction video to this PBSEons sort of brief history of geologic time video to kind of complement the Bill Wirtz history of pretty much everything, I guess, video that I already did. Yeah, you'll see. There's obviously some strengths of this video that didn't come through in the Bill Wirtz version. Oh, and I guess just about my background, this is the Grand Canyon, so it's like a lot of time back there represented in those rocks. So I thought it was kind of cool.
The tale of life on Earth has been unfolding for about 4 billion years, and we humans are just
4.6.
the last word on the last page of that story, at least so far. And the vast stretches of time that are covered by the history of life can be hard for us to fathom. We rack our brains trying to imagine what a few hundred years looks like, let alone billions of years. And like speaking for myself, I can't even remember what I had for breakfast this morning. So to help us really appreciate the full expanse of time, scientists have turned to the rocks. By looking at the layers beneath our feet, geologists have been able to identify and describe crucial episodes in life's history, from bursts of evolutionary diversity to disastrous extinction events. These key events of new life and sudden death frame the chapters in the story of life on Earth. And the system that we use to bind all these chapters together is the geologic timescale.
Eons.
First, let's talk about the history of geologic time itself, because figuring out how to read history in rocks was not easy. For much of human history, of course, we had no idea how old the Earth was or what actually happened in deep time or what happened in what order. But in 1669, Danish scientist Nicholas Steno published the first laws of stratigraphy, the science of interpreting the strata or layers of rock in Earth's outer surface. Steno argued that the layers closer to the surface must be younger than the layers below them. So the farther down you dig, he thought, the older the fossils are that you find there. Sounds legit, right? But in Steno's day, when some people thought that fossils had literally fallen from the sky for some reason, this was a pretty revolutionary idea. Building on Steno's ideas, Italian geologist Giovanni Arduino went a step further and began naming the layers of rock. In the 1760s, Arduino studied the Italian Alps, organizing their layers based on their depth and composition. The lowest layers of metamorphic and volcanic rocks he called their primary layer. Above those were hard sedimentary rocks, which he called secondary, and the top layers of softer alluvial deposits he named tertiary and quaternary. But because rock layers don't appear in the same order all over the world, there is no way for geologists to compare rocks from one location to another. Without a way to compare strata, there could be no universal timescale. Finally, in 1819, English geologist William Smith figured out the solution to this problem: fossils. By comparing the remains of ancient organisms from different rock formations, Smith could match their ages regardless of how far apart they were. For example, Smith realized that fossils of many early species of trilobites are found below ammonite fossils, which are in turn below certain kinds of shellfish. So any place in the world where you find these first trilobites, you know that you're looking at rock that's older than when ammonites lived. And even in the most ancient rocks that have little or no evidence of life, scientists can still look for signs of the...
So just really quick, he actually uses the term index fossil later on in the video, but that's the concept of index fossils that he's just describing.
very earliest major geologic events, like when continents first formed, and even when the Earth itself cooled and solidified. Thanks to the work of early geologists like Steno, Arduino, and Smith, modern scientists have used these and other clues to create what we now call the geologic timescale, or GTS. The GTS has been reworked many times to reflect the latest knowledge of Earth's history, and today it's organized into 5 subgroups: eons, eras, periods, epochs, and ages. Organizing time in increments like this allows us to ask questions about history on different scales. In the largest increments, like eons and eras, we can ask the biggest of big picture questions, like, was there life on Earth at this time? If there was, what did it look like? Did it live in the water or on land? This is the kind of top-level view we're going to take today. But the smaller increments of time, like periods and epochs, help us take a tighter focus and ask more specific questions, like, what was the climate like during this window of a few million years? And how did life around the world adapt to it? We'll be talking about those in more detail in future episodes when we talk about each era, period by period. Okay, so let's get the biggest of big picture views of Earth's history right now by taking a tour of all the eons and eras in the GTS. Eons are the largest slices of time, ranging from 500 million to nearly 2 billion years long, and the earliest eon is known as the Hadean. It begins with the very formation of the Earth itself, around 4.6 billion years ago, and ends 4 billion years ago. And this is the only eon that doesn't have any fossils, because back then, the world was just hell. Named after the Greek underworld Hades, the Hadean lived up to its name. The planet was racked by volcanic activity, cosmic...
Super important that they include the camera shutter sound effect for these photographs of the Hadean. I don't know, it's a little like, here's a postcard from the Hadean that's like a picture I took, I guess. Unclear why they did that. It's very funny though.
with bombardments, raging storms, and temperatures that were at times hot enough to melt rock. But even in this searing wasteland, life may have been able to form. While no fossils have been found from this eon, small amounts of organic carbon have been discovered in Hadean rocks that some experts think is evidence of the earliest life. These first organisms were tiny and single-celled, but they were eventually able to shape the future of the entire planet. So their appearance is the one major benchmark of this eon. The Hadean was brought to an end by the cooling of the crust of the Earth, setting the stage for the continents to eventually form. And this cooling marked the beginning of the next phase, the Archean eon, which ran from 4 billion to 2.5 billion years ago. Named from the Greek word for origin, the Archean was once thought to be when the first signs of life appeared. But at the very least, it's fair to say it was the first time that life flourished, forming massive microbes in the primordial seas. The fossils that these microbes left behind are called stromatolites, or sometimes stromatoliths. And the very oldest of them, like those found in Western Australia, date from the Archean. During this...
Oh, super random. I told you all in class in the beginning of the semester that there are still stromatolites in Shark Bay, Australia, which is kind of a hypersaline environment. You know where else there's stromatolites? Green Lakes Park, right around here. So stromatolites is just kind of a bacterial mat that's layered along with sediments. So it's kind of a biosedimentary structure, and you could argue that there's some microbial structures in Green Lakes that are stromatolites, essentially. So yeah, if you want to see stromatolites, you can. Well, actually, I don't think you can go scuba diving in Green Lakes, but they're there.
Time the atmosphere was mostly carbon dioxide, but the appearance of cyanobacteria was about to change all that. Then, 2.5 billion years ago, the Archean gave way to the Proterozoic eon, meaning earlier life. And around this time, photosynthetic bacteria, along with some multicellular forms of life, spewed tons of oxygen into the atmosphere. This probably wiped out most of the anaerobic life on Earth, but...
So just quick caveat to that. So he's condensing 2 billion years of photosynthesis into that, a bunch of photosynthetic organisms spewed oxygen and then everything died. So again, some of the earliest fossils that we know of are stromatolites, which were probably formed by cyanobacteria, which were probably doing photosynthesis. And some of those date back, in our geologic timescale to like more than, to potentially up to 3.7 billion years ago or something like that, if you include sort of molecular traces. And then there wasn't really a ton of oxygen in the atmosphere until like really 2 billion years ago or something like that, or like 1.8 billion years ago. So it wasn't just like a kind of flick of a switch sort of event. There's a lot of banded iron formations that had to form as the oxygen reacted with iron in the atmosphere. So it really was, it was a little bit more of a protracted period than he's giving it credit for.
It cleared the path for crucial new organisms, including the ancestral eukaryotes.
Look at that nucleus.
Nucleus and organelles wrapped up in membrane.
Such
Eukaryotes
a good
developed into the
nucleus.
first really big, complex, and sometimes kind of weird forms of life, such as the frond-like Carnea and the plate-shaped Dickinsonia. These new, larger organisms quickly diversified, and by 541 million years ago, we were at the doorstep of the next and current eon.
So those two taxa that he just showed pictures of are sometimes called the Ediacaran fauna, and they lived right before the Paleozoic. So around 635 million years ago to 541, this period of time. And again, this cryogenian period was when there were potentially two snowball Earths that happened one after the other in fairly rapid succession. So this was really exciting geologically. And then the Ediacaran period was when there are some organisms that seem to be related to nothing that we have alive today, but there are some organisms that seem to be in modern phyla. So there's potentially a mollusk, for example, in the Ediacaran fauna, and they're almost certainly sponges during these times as well, as you remember from the sponge video. But we're about to get into the Paleozoic, which is the first major part of the Phanerozoic eon.
Phanerozoic. Its name means visible life, and the Phanerozoic was when life really became obvious. This is the eon that's home to trees, dinosaurs, newts, aardvarks, us humans, basically life as we know it. Whew. How you holding up? You doing okay?
I'm doing okay. Yeah, so Phanerozoic is all these three things on this geologic timescale. Where am I? Okay.
We've covered about 3.5 billion years already. Just got another 500 million to go, and then we're home free.
Yeah.
Okay, now from here, it's best to explore the Phanerozoic eon through its eras, the next level down in the divisions of time.
Meh.
This will let us explore more recent history in greater detail. The first era of our current eon is the Paleozoic era, which began 541 million years ago. This chapter was defined by the diversification of visible life, and it started with a bang, actually an explosion, the Cambrian explosion. This rapid growth in diversity and complexity in the world's oceans is such a huge deal in the history of life that all the eons that came before it, the Hadean, the Archean, the Proterozoic, they're all collectively known as the Precambrian. At the start of the Paleozoic.
So it's basically because there aren't a ton of fossils of multicellular organisms that sometimes we talk about the Phanerozoic versus the Precambrian, and we just lump all the other eons into the Precambrian. In case it wasn't obvious before, the geologic timescale is made up of parts of variable lengths. It's not just like 100 million years is always an era, for example, or 100 million years is always a period or something like that. All the periods and epochs and eons have different have different durations in time, because they're defined by similarity of the organisms that are in there. So the reason that we have more fine divisions in the later part of the Earth's history is because we have more detailed fossil records, so we can make more fine divisions. Because if you remember from the origins of where the fossil record came from, it's based on kind of the concept of index fossils, really.
Over about 25 million years, the fossil record suddenly reveals the appearance of complex animals with mineralized remains. Hard parts, shells, exoskeletons, that kind of thing. And the very first of these new animals to become truly widespread were the trilobites. They were so common all over the world that they've been used as index fossils for the Paleozoic era for centuries, ever since the days of William Smith. But the trilobites soon had competition. Fish developed teeth and jaws and came to dominate the seas, including the first sharks and armored giants known as placoderms. Meanwhile, the land, which had been barren since the formation of continents back in the Archean, was finally being populated, first by plants and then by arthropods. By 370 million years ago, entire ecosystems had developed on primeval continents. Soon after, the earliest amphibians evolved and hauled themselves out of the water, leaving their first vertebrate footprints in the mud. 299 million years ago, the supercontinent of Pangaea had formed, with an enormous desert at its center. This desert was quickly populated by the ancestors of what would eventually become reptiles and mammals, which could thrive in dry conditions, unlike amphibians. But this time of incredible growth couldn't last forever, and instead, the Paleozoic era ended in cataclysm. 252 million years ago, 70% of land vertebrates and 96% of marine species disappeared from the fossil record, including survivors of previous extinctions, like our friends the trilobites.
Yeah, no more trilobites. Womp womp.
I still miss those guys.
Me too,
The
dude.
event known as the Great Dying was the most severe extinction in our planet's history, but its exact cause is still unclear. A possible meteorite impact off the coast of South America might be one clue, and in Siberia, layers of basalt show that massive volcanic eruptions covered large swaths of Pangaea and lava. Both of these incidents coincided with the end of the Paleozoic, and it seems more than likely that the extinction had many causes. In any case, the Paleozoic may have begun as a chapter defined by an explosion of life, but it ended in nearly absolute death. It took millions of years for life to recover, but when it did, a new world, the Mesozoic era, had arrived. This is often called the Age of Reptiles, and with good reason. Right from the start of the Mesozoic, reptiles were incredibly successful. This is when they took some of their most famous forms, like dinosaurs, pterosaurs, and a variety of marine species. In fact, all of the non-avian dinosaurs lived only in the Mesozoic, so they remain one of the best index fossils of this era. And many modern groups of organisms also evolved in the shadows of the reptiles, like mammals, frogs, bees, and flowering plants. But the Mesozoic era came to it.
So that's a lot, right? These videos tend to focus more on the charismatic megafauna because they're geared at the general public, and that's fine, and obviously they're really well done videos. But I'm going to try to talk a little bit more about the fact that the Mesozoic was a really, really important time for things besides dinosaurs as well.
Would end 66 million years ago with yet another episode of devastation, this time known as the Cretaceous Paleogene or KPG extinction event. Like all mass.
Yeah, sometimes it's abbreviated KT, sometimes it's abbreviated KPG, sometimes people call it the end Cretaceous extinction, but it's all the same thing.
Die-offs, the KPG had many causes, but probably the biggest of them was a giant asteroid that struck the Earth, sending enormous amounts of ash into the atmosphere, blocking out sunlight, and creating a vicious cold snap across the planet. Without the sun's energy, entire plant communities died, and the animals that relied on those plants perished with them. Evidence of this impact can be found in the layer of iridium in rocks dating to the end of the Mesozoic. Iridium is an element that's rare on Earth, but very common in asteroids and comets. And a giant impact crater in the Gulf of Mexico, whose age matches the date of this extinction, has become the smoking gun for the asteroid hypothesis. The victims of the KPG extinction were some of the biggest reptiles of the land, sea, and sky.
Stegosaurus was in the Jurassic, dude. That's boo. Boo! Stegosaurus was a Jurassic dinosaur.
Including all of what we now call the non-avian dinosaurs. Birds, of course, survived the cataclysm.
Birds are dinosaurs.
Making them the last surviving lineage of the dinosaurs.
Yeah.
Okay, we have 66 million years to go, and that's the last major extinction event that we have to talk about. I thought you might want to freshen up, so I bought these pre-moistened towelettes.
Oh, cool, thanks.
It's going to... You have some iridium here on this side, on your forehead.
On this,
side.
over
With
here?
all the reptiles gone, the smaller animals that remained were able to eke out a living in the next era, the Cenozoic. This is our era, in more ways than one. It's the era that we're in today, and it also marks the rise of the mammals. Soon after the KPG extinction, the climate warmed, and jungles stretched across the planet. Mammals quickly recovered in this hothouse world, and by 40 million years ago, most of the mammal groups that we recognize had come about, like whales, bats, rodents, and primates. But starting around 34 million years ago, the climate began to shift again. This time, ice caps started to grow at the poles, taking up much of the planet's water. And these drier conditions...
So you remember from the Antarctica video that Antarctica wasn't always glaciated. And in fact, it wasn't really until 30-something million years ago that glaciers really became dominant in Antarctica.
Created a new habitat, the grasslands,
Grasslands.
where ancestral horses
Super cool.
and antelope were hunted by the first cats and dogs.
Totally
It was
awesome.
also in these grassy plains, 7 million years ago, that a species of ape called Sahelanthropus became the first known primate to walk upright. 2.6 million years ago, the ice caps expanded even more, and the Earth entered a glacial period. This is the one you hear referred to as the Ice Age. Over the course of these last several million years, most modern life forms that we know about developed and thrived, alongside giants like mammoths, ground sloths, and saber-toothed cats. Once again, though, this era of diversity came to a morbid end. Starting around 15,000 years ago, the climate began to warm up, and over the next few thousand years, many of the giant fauna went extinct. By 11,700 years ago, the last major glaciation was over, and modern humans inhabited nearly all the corners of the globe. But how big a role we played in the extinction of the so-called Ice Age megafauna is hotly debated. Regardless, there's...
Super hotly debated. If you all take mammalogy or biogeography with Lamalino, he is very much in favor of the overkill hypothesis. He's very much in favor of the idea that humans had a really dominant role in the extinction of a lot of megafauna in 15 to 20,000 years ago. As someone who's done work on islands, island systems show really, really clear evidence over and over again, just repeated dozens of times across the Pacific especially, that as soon as you see pottery shards and ash from fires, you stop seeing a lot of the endemic birds especially. So, when the ancestors of the Maori people colonized New Zealand, when the ancestors of the Hawaiian people colonized Hawaii, you stop seeing certain, especially flightless birds and stuff like that. So that seems to happen over and over again when humans arrive. So people try to apply that to North America, for example, and South America, and it does seem like there's some concordance with the arrival of the first humans in North America and the extinction of a lot of really big animals. The climate was also changing super duper rapidly at that time period, and the reason that some people don't think climate change was as important in driving the extinction of these organisms is that the climate had cycled really rapidly several times before that. So there have actually been kind of 4 or 5 glacial and interglacial events throughout the Pleistocene, so throughout the past 2.7 million years or so. And the megafauna didn't go extinct then. And also a lot of these megafauna, they're able to disperse really far, and many of them have really, really big ranges. So like if your natural range is from Texas to Canada, is climate change going to make you go extinct necessarily? If you're, if you have such a big geographic range, you should be tolerant of different climates, and you should be able to, move, especially in the central plains like that. And climate change should, we would think, drive the extinction of smaller organisms as well. It wouldn't be biased towards larger organisms. So so that's the argument in favor of the Pleistocene overkill hypothesis, but it's still debated, and the answer might be different depending on which continent you're on. So Australia also had a big die-off in its megafauna that is sort of correlated with the arrival of the first Australians, but it's not as tight of a correlation, and so people might think that the desertification of Australia might play a bigger role in those extinctions. Still an active area of research. Super duper cool.
There's no escaping the fact that our species has shaped the Earth to its will since then.
True
Like
that.
cyanobacteria and the dinosaurs before us, we've had a huge impact on habitats, other organisms, and the biosphere itself. And as we've learned today, it's the most dominant forms of life that define each phase of deep time. So even though our time on this planet amounts to the last word on the last page of the story of life, we are the authors of the next chapter. One day, the epoch of humans may be detected by the marks we make on the land, the traces of our cities and farms. And our very bodies will be the index fossils of this time. No matter how our chapter ends, we get to be characters in a truly amazing story.
And you've all been characters in the truly amazing story of EFB 311. So thank you.